So when you're looking at these concentration examples, we want to be able to, instead of just using the words high and low, we want to be able to give a little bit more description of what we mean by high and low. Okay, that is tonicity. So tonicity is a comparative measure to compare two solutions. Okay, so we have solution A and solution B. Here's some fluid in there. There's my water and my water. In solution A, I have 3 molecules of sugar. In solution B, I have 10 molecules of sugar. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so I have 10 molecules of sugar. Ask yourself, which one has the higher concentration? That would be B. So what we call this, when we're measuring two different solutions, we say the one that has a higher concentration is called hypertonic. Hyper meaning many, tonic having to do with the concentration. Tonicity, this has to do with concentration between two solutions. So this one, this low concentration, we call this hypotonic. Well, what if we slapped a membrane in between these things? Now we can change these glass circles, or these glass things filled with water, and we can switch from A to B. Now we can say outside a cell and inside a cell. So we know that there's fluid all over the place, both on the outside and inside the cell. So now we're looking at these concentrations of molecules to determine tonicity. If we're hypertonic solution, that means that we have a lot of solutes on this side of the membrane, and we have a little solute on this side of the membrane. So we're back to low, high, low, differentiating between solute concentration and water concentration. I already explained how to see which one was high to low for water in this example. So in this example, what I'll do is I'll just say, if you can determine that a solution is hypertonic, hypertonic solutions suck water. So we've looked at this, we've identified this is high solute, this is low solute, which means this is high water, this is low water. That's the long way to figure out that water is going to move inside the cell. But if we want to remove all this stuff and just look at these solutions, well, we can say, all right, I know that this has more, that this is a more concentrated solution because it has more of these circles in it, so it's a hypertonic solution. And then we know hypertonic solutions suck water. So instead of just saying that for a third time, how can I remember this? What I like to think of is a 9-year-old child. You give a 9-year-old child a glass of soda, and here's a straw. And he's going to take that soda down from here to here in about 3 seconds. Okay? So I like to think of hyper kids, this 9-year-old child. He's really hyper, and he's sucking on his drink. Hypertonic sucks water. Hyper sucks liquid. So let's do another membrane, and then I'll ask you to choose which way water is going to move. I know I'm beating this thing like a dead horse, but we use this effect of tonicity throughout the whole class. So if I asked you, which way is water going to move? What are you going to say? You can do it one of two ways. You can label these as hypertonic and hypotonic solutions and use the phrase hypertonic solutions suck water. Or you can count your solutes here. You can put high to low, reverse it for water, and then see which way water moves from high to low. So let's do that way first. So if I'm looking at my solution, and I go, okay, this is high solute, so this is low solute. Well, if I'm looking at water, then that means this is high water, and this is low water. So I can move from high to low that way. The other way I did it was, well, let's define the tonicity of these solutions. And whenever I say, well, I know that this has way more solutes in it, I say this is hypertonic. Right there I can say hypertonic solutions suck water. So either way, we know that water is moving from this right side to the left side of the membrane. Okay, So we defined 3 different things. We defined if we do inside the cell, outside the cell. We do a bunch out here and a little bit in here. We say outside the cell is hypertonic to inside the cell. Another picture that we could do is out and in, and this time we have a ton inside the cell and just a little outside. So in referencing the outside to inside, we'd say that this outside solution is a hypotonic solution, which means water is going to move this way, because we know hypertonic solutions suck water, and we know water is going to move this way because hypertonic solutions suck water. Eventually you'll reach an equilibrium where you have outside and inside being the same. This is called isotonic. So you don't really get a movement of water here because you're already at your equilibrium. Let's see what happens when we put a cell in a certain type of solution. So let's draw our beaker. And I'm going to put a cell in there. And we'll see how sodium is going to move in this cell. So within this cell, we have 2 sodium ions. Outside the cell in the solution, we have too many sodium ions, so just a bunch. So if we have to ask ourselves, using those words, hypo, iso, hyper, if we're looking at the solution, not the cell, so we're looking at the solution, whatever we put our cell into, we want to determine the tonicity of that. So is this a hypertonic solution or a hypotonic solution compared to the inside of the cell? Well, we have more on the outside than we do on the inside, so this is a hypertonic solution. A cell is placed in a hypertonic solution, what happens? Well, ask yourself. With osmosis, hypertonic solutions do what to water? Hypertonic solutions suck water, which means water is going to leave this cell. When water leaves the cell, it can shrivel up and die. So let me draw that picture again. We had a bunch of NAs out here. And we had a cell that only had 2 inside. And these numbers are not realistic. You'd have hundreds of thousands or thousands of sodium ions in a cell. But then if we compare that to this picture, we know that water has left this cell, and I'll do that with a red arrow. Water has left this cell, so now we have more water out here, which means our cell shrivels up, and it's going to look like that's a shriveled up cell. So this, when cell goes into hypertonic solution, cell shrinks. Let's try a hypotonic solution. So I've got a beaker, and I have a cell, and in that cell I've got a bunch of sodium. And on the outside of that beaker I have a little bit of sodium. So relative to the cell, what is the solution? That's what you want to ask yourself always. Is the solution hypertonic or hypotonic? Hyper or hypotonic? Well, we see that we have less out there, so we have a hypotonic solution, which means we have a hypertonic cell. We know that hyper does what to water? It sucks water. So hypertonic solutions suck water. Inside this cell, we have a solution. Okay. So the hypertonic solution is going to pull water in. When you pull water in, it's going to swell and it can burst. So you do that. I've got water moving into the cell. Look at the cell on this size. Well, you can see it's gotten bigger because we've filled it with a bunch of water. And eventually, if you fill this thing with too much water, remember we just said water puts pressure on this plasma membrane, the cell can burst open and lyse and die. So you may have a question that says you're given a hypertonic solution. What is the cell doing? Is it growing? Is it shriveling? Is it staying the same? If it's a hypertonic solution, that hypertonic solution is sucking water out of the cell and the cell is shriveling. If it's a hypotonic solution, the cell is sucking in water and it's going to lyse and burst. If it's an isotonic solution, nothing's really happening. Alright, long video. So that is where we'll stop with this one.